Good morning. We're going to talk about odometry of a robot. The group is conformed by Eduardo Yepez, Alan Gonzalez, and me, Steven Almenaba. Odometry. Odometry is a fundamental technique in mobile robotics that allows estimating a robot's position and orientation over time based on data provided by its motors and heels. It is used on differential robots. We use odometry not only to know the precise movement of the robot, but also to evaluate its performance in real life. The kinematic model. It is based on the angular velocity of the heels and their contributions to the linear and angular velocity of the robot. We use a velocity vector, which parameters are the linear velocity and the angular velocity. We also use the velocity of each heel of the differential robot. And there is no velocity in the y-axis because of the constraint of kinematic model. Just as the kinematic constraint says, it's just a pure rolling in the x-axis, forward and backward, and there is no lateral sliding. In order to understand odometry, we use a Lego Mindstorm if3. It is designed to move following a predefined trajectory. MATLAB is used to programming it. Here are some characteristics. The heel radius is 2.75 centimeters. The axis length, the length between the two heels, is 11.07 centimeters. The degree of mobility is on the x-axis, forward and backward. The degree of steerability, it means the direction depends on the speed of each heel, and the degree of maneuverability is a two-dimensional plane in the xz plane.
Hi, my name is Eduardo Yepez, and I'm going to continue this presentation by explaining the code use and the path. The code used. Okay, this code is divided into 5 important structures that are setting physical parameters and initially the engine. The first movement, there is a 90-degree rotation. The second movement, there is a straight displacement of 0.2 meters. The third movement, there is a curved displacement, and the generating the trajectory graph. Okay, I'm going to explain each individual parts. Begin with the setting physical parameters and initializing the engine. In this part of the code, the only thing that matters is the physical part of the Lego robot which we work with. As already my partner explained the theory behind all this, this is only put the numbers of these physical parameters in the codes. That's all I do. Using the theory, the equations, and putting the physical parameters that we measured with the different components, putting in the codes, and that's it. The second part is the first movement of the degrees and rotations. With this part of the code, we wanted to reach that the motor, when the code is initially started, we wanted to make a 90 degrees movement. How do we do that? We configured each wheel, the speed of each of the wheel, and the trajectory of each of the wheel. It was very simple, as you can see in the notes within the code. Another thing, I will not be very specific explaining this code, and it's not 100% complete in this code. Why? Because if I explain it all, I will be here an hour, and I have a limited time. So if you want to see more specific parts of codes, you're welcome to read the complete PDF that we have of this practice. The second part is the movement, the straight movement of displacement of 0.2 meters. It's the same as the last part, but instead of rotating, we wanted to give a straight displacement of 0.2 meters, as the title already says. We control it with the path that is the WL trouble and WR trouble that is just a straight up movement. Now, the third movement is the most complete part because it's a curved displacement. As the title would say, it's, oh my God, it's so difficult. But no, it's actually very simple because the only thing that we wanted to upgrade, or saying those words, is the angle. And if you can see in the second In image, we see that in the WL trouble and WL trouble, that is the control of the right and left wheels, we only give an angle to rotate, and that's it. And with straight lines and with the angle rotate, it gives you the form that we want it. Now, for the generated trajectory graph, in every single part of this code, we summarize every single x and y data between the iterations. Each iteration was in a while sentence, and we obtain all this data, and in the end of the code, we make a graphic out of it. As you can see in the first image in the left, it is the graphic that we wanted. And with all this being said, we have the result that is right here in the video. And you can see that the first thing is rotating the model, then the straight line, then the curved line, and then we have the model moving forward back. This part is going to be explained next by my next partner. Thank you very much, and that's all for my part.
Hello, my name is Alan Gonzalez, and I will explain what we wanted to demonstrate in the theoretical trajectory and the experimental trajectory. Okay, in the experimental trajectory, the only thing that varies with respect to the theoretical trajectory is that it rotates a little bit more, and the objective was to rotate 90 degrees. And in the last session, once the curve was made, the robot continued to move a little bit more than what was initially programmed. Both errors caused it not to be exactly the same as the theoretical trajectory. Okay, now for the conclusion, we in this project we have concluded on understanding and implementing differential robot odometry, evaluation of trajectory accuracy and sources of error, and enhancing odometry with additional sensor for improved precision. Okay, so this was our project, and thank you very much for your attention. See you later.